Well, welcome everyone. Thank you. Firstly, I would like to thank you all for joining this session. And let me first introduce myself. My name is Armando. I work for Blue Harvest, the engineering unit of Capgemini. I am from Spain. My background is mainly in software engineering. I have spent quite some time building software applications, mainly in Java language. And last year, I moved to the Netherlands. I came originally for the weather, but I have decided to focus back on my career. So here I am sharing a bit of the knowledge I have gathered during the last year working with Kubernetes and cloud-native stuff. Demystifying Kubernetes and container orchestration. I'm not actually that happy about that word I came up with, so I will try to explain a bit what it does mean in other words. The goal of this session is go through the topic of container orchestration and Kubernetes with some kind of helicopter view in such a way that any engineer without a specific background in systems administration or containers or Kubernetes can grasp the topic, but also show you how we can easily get fully operational and professional setup with a demo that we have prepared based on Terraform, Kubernetes, Elastic EKS. So agenda for today, I'm first going to introduce the topic of container orchestration. Let's see which is the problem that we are actually solving with this nice thing of container orchestration that is so popular. Later on, we are going to dig a bit deeper into Kubernetes as a container orchestration to see how it works. I'm going to simplify a lot of things in this explanation to make it feasible to do it in 15, 20 minutes. And later on, we are going to do a demo in which I'm going to trigger a pipeline. We're going to provision a high available cluster on AWS with 6 nodes, and we're going to play a bit with it, see some things like logging aggregation or how we provision some components that we need to have in order to operate our cluster. In order to do that, since obviously that would take quite some time, I'm going to kick this pipeline that I mentioned right now. So by the time I finish with my slides, it should be already created. Yes, 1 second. Yeah, it's working, so I can come back to my slides. Yeah. So let's start them. Here I put a definition of container to clarify just if someone is actually entirely new to the topic. I'm not going to read the definition. I think that like most of the definition, it lacks something. It's very difficult to come up with a perfect definition for something. But it touches a point that I believe is key when we talk about containers in general, Linux containers. Isolation. But why do we love having isolated things in computers? Well, for starters, we get portability. So we can wrap something within a container, and we can run it wherever we want. We can run it in our laptops, in our CI/CD environment, in our staging environment. So that increases developer productivity in a lot of ways. Our developers now can wrap something and ship it to production, so we avoid this kind of problem that it runs in my machine, it doesn't run in yours. And from an operational point of view, we also simplify a lot of things like environment configurations, dependency management, by wrapping and shipping our applications as containers to production. Plus, we also simplify scaling our applications if we have a thing that we can actually replicate as a whole. There are, of course, many other advantages and many other reasons we containerize applications, but let's go to the challenges that we have when we start doing this. Firstly, we need to figure out on which nodes, on which actual machines we're going to run those containers. I just said that it's easy to scale because we can just replicate them, but we want more than that. We want that to happen automatically, the famous auto-scaling thing that we see everywhere. And we also want our containers to self-heal, okay? If one container fails, or if one entire node fails, we want that the containers running on that node to pop up on another node that is working properly. And we need as well some help to roll out rollback changes in our environment, and many other things that I'm not gonna go through here. So in order to solve these challenges and many others, we have what we call container orchestration. So we head a bit towards the main topic of the talk. There are many tools to orchestrate containers to do the job out there. You can, some of them more customizable, some of them more as a package. But in the last years, one of them have become really, really popular, Kubernetes. How many people here are using Kubernetes? Okay, not even half of the room, so I think that it's the right audience. Kubernetes was born at Google based on the experience they gathered with a cluster management tool they had called Borg. Since its version number 1, it has been part of the CNCF, so it's not actually a Google product, as many people think. And during the last, I think, 1 to 2 years, it has become one of the most popular orchestrators out there. And now, with the recent release of EKS from AWS, most of the big cloud providers are offering some kind of Kubernetes as a service flavor in order for you to orchestrate your containers on their infrastructure. This was some kind of introduction to the topic, so let's now go a bit deeper into how Kubernetes works. In Kubernetes, we will have master nodes, and we will have also worker nodes. The master nodes run the control plane, the brain of our Kubernetes cluster. And on the other hand, our worker nodes are the ones that are going to run our actual containers, application containers. Of course, we want our worker nodes to be high availability, to have more than one node, to have auto-scaling at the node level as well. But also, we want our master nodes to be resilient as well, because otherwise we couldn't operate our system against a failure. If we zoom in a bit into what we have within a master node, we will find something like this. This is, again, a simplified version of the Kubernetes architecture, but I think that contains some of the key elements. Starting from the top, we have the Kubernetes Rest Api. And this is just as any other REST API that you guys have built. A REST API is exposing as resources everything that we want to manage in Kubernetes. So anything that we're going to tell Kubernetes to do is going to be through resources via this REST API. This API server, REST API server, is a completely stateless component as a good REST API. That brings us to another component that we have bottom right in this picture, which is etcd. Kubernetes stores all the resources that we are going to create in our cluster in distributed key-value storage that probably you guys know from other things because it's not Kubernetes specific, called etcd. So in order to make our master high available, we need to take care that our API is high available and our etcd storage is high available. Another two components we have in this picture are the scheduler and the controller manager. A scheduler job is to decide for each container we create in our cluster on which node it's going to run and enforce that. We can, of course, give hints to that scheduler to make some decisions and some choices based on our own interests. It's not some kind of random or scheduling. And on the left, we have the controller manager. Like any other real-life manager, the controller manager doesn't do anything by itself. It delegates everything to controllers. These controllers are a key piece in Kubernetes. Controllers are the ones managing the lifecycle of the actual Kubernetes resources. So if we look into this picture again as a whole, we are going to create resources in Kubernetes through this REST API. Those resources are going to be scheduled in our etcd storage. We will have a controller for each of those resources. That controller will do stuff that we need to do in order to make happen what we need, what we want to happen. And the scheduler will take care of, decide in which node we're going to run our containers. There are other components in the master architecture, but I think that this is a good summary. So this was the master node. Let's have a look now to what we have on the worker node. I didn't put it in this picture, but of course in our worker nodes we will have a container runtime, also in our master nodes most of the time. By container runtime I mean Docker, Rocket. I guess how many people here have used Docker or Rocket or any container technology? Okay, that's good. So we will have our actual container runtime running in our worker node, but however, it's the kubelet job to tell the container runtime what to run based on the resources that we store in our etcd data storage. That kubelet is usually an operating system service running in our nodes, okay, really getting information from the master and making our containers run depending on the, okay, we have Docker, Rocket, whatever. I put here the name of pod. I haven't explained that. Probably you guys have heard of their Kubernetes pods Kubernetes. I'm going to explain right now the abstractions that we have in Kubernetes, starting by the pod. The pod is basically an abstraction that we are going to use to abstract the container. We can have more than one container in a pod, but for now, let's not get there. Let's think about the pod as a container. And I'm missing still a component in this picture, which is kubelet. Sorry, kubeproxy. Kubeproxy is a networking component. I have a couple of slides later on about networking, but let's, for now, so we keep the level of abstraction of the talk, let's say that kubeproxy makes an important part of the Kubernetes networking happening. And it's running also in our worker nodes. So sometimes it's also running on our master nodes. It depends on the setup. So this was a technical overview of the stuff that we have running on a Kubernetes cluster, of course, skipping some details. Let's have a look now to the main abstractions that we're going to use in Kubernetes to orchestrate containers. I have mentioned already that we are going to tell Kubernetes everything through a REST API by creating resources in that REST API that are going to be storing our etcd data storage. Let's see which are those resources. Starting by our own nodes. So the nodes that we have in our cluster are going to be also Kubernetes resources. So Kubernetes can actually, the scheduler can actually manage the nodes that we have, which of them are ready, which of them are not ready, which is the version of Kubernetes running on each node, stuff like that. Of course, we will have our containers running on our nodes, abstracted by the concept of pod. A pod can have more than one container, even though typically you will find there only one, but there are certain patterns that require more than one container running within the same pod. In order to tell Kubernetes which pods we want to create, we have different abstractions. One of the most used abstractions to achieve this is the deployment. So this is another resource, an important one that you will see all around the internet in most of the Kubernetes examples. It's a high-level abstraction to deploy containers to Kubernetes. In the deployment, we will specify things like the actual container we want to run, the number of replicas we want for that container, stuff like volumes, configuration, environment variables, if we want more than one container. What will happen underneath is that, as I mentioned before, we will have some controls running in our cluster, managed by that component that I mentioned, the controller manager. And among those controllers, we will have the deployment controller that will manage the deployment object. And the nice thing about these controllers, guys, is that they talk to each other. So this deployment controller, for a specific deployment, will create another resource called replica set that you guys probably will see out there in the documentation if you start looking into this. And that replica set will have also a controller that will take care of manage that the replicas that we specify in our deployment are running as we want, as they should. This sounds cool, but the thing with pods is that they are ephemeral components. We scale them up, we scale them down, they come and go. so we cannot rely on them entirely. For that, we have the concept of the service in Kubernetes, which is also an abstraction. There are different types of service and a lot of variants of this concept, but let's focus on the basic Kubernetes service, which is the default, the type of service default. Let's put an example for this. Let's say that we want to deploy an Nginx application on Kubernetes. We define our deployment, in which we specify that we are going to use a Docker image for Nginx. We want two replicas, and we're going to set a service on top of those pods. That is going to help us to abstract a set of pods performing the same task, and also implement some kind of load balancing going on in there. Besides that, we will have another resource called Ingress. Ingress is a resource that we're going to use in order to bring external traffic into our cluster. And when we start looking into the Kubernetes concepts and abstractions, this sounds not entirely intuitive at first. Because we have already a service, why don't we use the same service? So to explain this, I think that it's important to have a look also into how Kubernetes networking works. I only mentioned some of the Kubernetes abstractions, but later on, when we see our demo, we can go over some other abstractions on top of the Kubernetes dashboard and with kubectl and see them in action. Kubernetes networking sounds a bit scary at first when you say it like that. So it's Kubernetes networking. Sounds like a pretty big deal. And to be honest, I don't think it's an straightforward topic at all. But let's try to walk through it in the way I think is more natural for everyone to understand a network. We will have nodes in our cluster. Of course, we want more than one node. That brings us to our nodes network. That's the network that we all know, so our computer's network. If we think about a cloud provider, that's our cloud provider network, our VPC in AWS, the name that you have for that in another cloud providers. On top of our nodes, here's when things get a bit more complicated, we will have our container, abstracted as pods again. And they will run on different nodes. There is one thing about Kubernetes networking that is some kind of requirement, which is that any pod running within the Kubernetes cluster should have an addressable IP from any other node running within the cluster. It doesn't matter on which node it's running. So that brings us to the pods network. So we need to, on top of the network that we already know, we need to have a second network that is going to be our pods network. Said like this doesn't sound difficult, but it's not that easy to achieve. Okay, if you go to AWS, you have already a network in place, and now you want to have a second layer of networking. The thing is that Kubernetes doesn't have a strong opinion about how this is implemented. On the other hand, it relies on a standard called CNI, Container Networking Interface, which is something like, I'm going to ask you for an IP for this pod, and you're going to give me an IP for this pod. And there are different implementations for that contract, for that standard, and depending on the setup you guys have, you are going to use one implementation or another. And that's a design decision that you need to make when you design your Kubernetes infrastructure. If you deploy a cluster out of the box, by default, you will get some very basic plugin. If you go to one cloud provider, you will need one specific plugin for that cloud provider, depending on your requirements. I think that for now, it's quite enough information about that. But we have left something out still. So we have also the concept of the service that is going to be abstracting a set of pods performing the same task. Service may span pods running on different nodes. And we will have, of course, multiple services running in our cluster, because we love distributed systems. We like to create a lot of services. Then this brings us a third networking layer, which is the services network. The services network is implemented by Kubernetes itself. It ships with one component taking care of the services network, and that's the component that I skipped before, called kubeproxy. So that's a component running on each Kubernetes node, taking care of setting IP table routing entries on all your nodes. So anytime you request a service IP, the node knows to which pod it has to be routed. And that's how the default service, the most basic and fundamental service in Kubernetes works. So if we think about this now, and we think about the initial question of why do we need an ingress, why do we need an extra resource in order to bring traffic to our cluster, there is no way that from my mobile phone, from any of your devices, you guys can reach one of these services, because your device is not a node in the cluster. So it's not running kubeproxy, so it doesn't have the IP table entries to reach my services. We need something else. We need some load balancer kind of thing within our nodes network that is also able to reach our services. And that used to be typically the ingress controller that is going to create mappings for the services based on the ingress resources that we have. So it's kind of the same pattern, concept plus controller that manages that concept, but in this case, the ingress controller has a lot of responsibility. So that's one of the reasons you will find a lot of discussions and blogs and things around the concept of deploying and setting up an ingress controller. And there are, of course, many options depending on how you want to bring this traffic into your cluster. If you go to Google Cloud, you will get a Google Cloud Load Balancer out of the box as an ingress controller. So every time you create an ingress, you get a route from your Google Cloud Load Balancer into your cluster. So if you go to AWS, for example, you don't have anything out of the box, so you need to set up something. It depends on your setup. I think that we have kind of enough theory so far for Kubernetes, concepts networking, so let's move a bit towards some more real-life Kubernetes stuff. Let's have a look to how it would look Kubernetes setup on top of AWS. And again, I'm missing quite some details in this picture. Starting by the top, in which we will have some EC2 instances for our master nodes, running the Kubernetes API. For what we will need as well, a load balancer in there. So we can actually reach our Kubernetes API, and we can have our Kubernetes API in high availability. We said that our master nodes run also distributed key-validated storage, called etcd. So we need some persistent storage for that. That's going to typically be some elastic block storage on AWS, for example. And an important thing about that is that we need to back up that, we need to manage that, because if we lose our etcd information, we are losing our entire infrastructure information. So we are basically in a very bad situation. Gonna be okay. So, and of course, for our worker nodes, we will have as well some EC2 instances. With important detail is that those EC2 instances need to be registered in the Kubernetes cluster as nodes. So it's not just spinning up EC2 instances. We need to install, of course, the Kubernetes components and so on. If we go, for example, for using the AWS container service, EKS, recently released this year, we get all these two layers for free, or not for free, as a service. Okay, so, but we don't have to manage our etcd storage. We don't have to manage our Kubernetes masters, but we rely on AWS for that. So it's again the trade-off: do it yourself, get it as a service. You lose a bit of flexibility. You get more time, save some money, maybe. And we still need to take care of our worker nodes. That's something that on EKS, AWS has kept as the previous service they had for containers, is that you manage still your worker nodes. So how do we get something like this deployed very quickly? Because I triggered a pipeline before, but how do we actually achieve this? If we want to go the way we manage our masters, we manage our etcd storage, we take care of the version that we have on our etcd storage, we back it up, so on and so forth, we can use a tool called kops that we have available out there. And by running just a command like this, with some options that I skipped for simplicity, we can get an entire high availability cluster running in AWS. I'm specifying here I want 3 master nodes, that I want 5 nodes. I want WIF as my CNI implementation. That WIF is the plugin that is going to implement the pods network that I put in my picture before. I'm specifying the network I want to, the nodes network I want to running on. a DNS to create some entries for my API, and more stuff. If we want to go the way we use EKS, for example, on AWS, we can leverage this Terraform module. How many people are familiar with Terraform? Well, how many people are familiar with CloudFormation? Basically, we're talking about infrastructure as code. CloudFormation is AWS brand infrastructure as code. Terraform is more generic. We write some script, we give it a tool, and that tool will create the resources on AWS by talking to the AWS API. And it's modular, so we can reuse a Terraform module that is already available called EKS that will take care of creating all our master nodes, our EKS cluster, our worker nodes. The thing with EKS is that we pay by cluster hour, so we are not aware of what AWS is running there. They commit to give us high availability, and we believe that. So, well, that's it. Not actually. So with that, you guys can get a cluster up and running. But there are a couple of things more that you may want to consider in order to have your cluster fully operational. We've mentioned that one of the cool things that we have with this entire thing of containers, Kubernetes, is scaling and auto-scaling our containers. But out of the box, if you create a Kubernetes cluster, you don't have everything you need to do that. You need to set up a couple of components in order to get that ready. Also, we don't have enough visibility if we create the cluster out of the box. By visibility, I'm talking about having a dashboard when we see graphically what we have, having some metrics, some log segregation, things like Kibana, ELK stack, things like that. We want them out of the box, click the pipeline, have the cluster running with all of that on top of it. And I've been mentioning the importance of having a proper ingress controller running. That also, we don't have it out of the box, so we need to set up that as well. Plus, we may need some also identity access management. I think we do need some identity access management. The only thing is that if we go for EKS, AWS enforces that we use AWS as identity access management. If we go for, we manage our own entire Kubernetes cluster, we can set up our own identity access management, or we can integrate it with AWS as well. How do we get this, or which packages we need to enforce these features? Well, in order to set up auto-scaling, there are different components, but we will need at least to make Kubernetes aware of the metrics that we have in our system. That means CPU memory consumption of both our pods and our nodes. And we need to link Kubernetes to our cloud provider. So for that, we need to install a component called cluster autoscaler. And for the metrics, there are different options. We have, there is a component called Hipster with InfluxDB as storage, but now it's becoming quite a practice, a common practice using metric server, which is like the canonical implementation of the Kubernetes metrics API. Plus, for visibility, what we have set up in this example, in this demo that we're going to see just in a moment, we will have, there is a Kubernetes ships with a dashboard, but it's not automatically installed, so we need to install the Kubernetes dashboard. We also want some FK stack, Elasticsearch, FluentD, Kibana. That's kind of ELK stack, but shifting log stash by FluentD. And the combo Prometheus Grafana, this is quite helpful as well. In the sense of bringing traffic into our cluster, we need to set up ingress support. So for that, what we are doing in our example is installing an ingress controller, an Nginx ingress controller, which gives us some kind of portability as far as we can get portability running on a cloud provider. And also we are setting up a couple of nice components in order to provide automatic DNS integration and automatic certificates issues for all our ingresses. We're going to see that in practice right now. Plus, also we can set up this component if we want to get our AM integrated with AWS. That means that you only manage one set of credentials. You don't need to manage Kubernetes users plus AWS users. You authenticate in Kubernetes with your AWS credentials. So that's the picture of the things that we're going to install on top of our Kubernetes cluster. How do we get that done again? Well, there is a cool tool out there called Helm that will help us with this. Helm is the Kubernetes package manager. So basically, a Kubernetes package means a bunch of configuration packaged in an artifact called a chart that we can also parameterize. So I can run a command like this and install on the top of my cluster my Kibana application and parameterize more things than that. Okay, I can also parameterize the DNS, the ingress configuration for Kibana. Also for Elasticsearch, there is a chart out there, so you can guys install an entire high-level Elasticsearch cluster with 8 nodes by running a command like this. I don't have the example for Elasticsearch in the slides. And that's it for the talking. So demo time. For the demo, I'm going to go to this pipeline that I just triggered. You guys, well, I'm having an issue here with the screen. Yeah. I think that I'm going to fix this quickly before we move forward, because otherwise it's going to be hard for me to demo like that. Well, I'm going to try because I don't find out the option. So this pipeline that we see here is the one that I just triggered before. And basically what we are doing is, after testing our infrastructure as code, we are running our Terraform scripts in this deploy job. That's creating our EKS cluster in Kubernetes, in AWS, and also our worker nodes, some VPC configuration. And on the second job install, we are installing all the Helm charts that we saw in the picture with the blue boxes. I really need to fix this because my screen is not the same screen that you guys are seeing. So. I may use some help here. Okay. Yeah, sorry for that. So now we're seeing the same thing. Yeah. Okay. Well, let's see if we created our cluster on EKS. Okay. Yeah. Over here. Yeah. Good. We have our cluster called JFall. One thing I need to do to actually show you this cluster in action, it's download some configuration that I have created here in my pipeline. I'm going to quickly set up my developer machine. So I have 2 files here. One of them is my kubeconfig file, and the other one is a BPM configuration file that I'm also setting up in this pipeline in order to have private resources like Kibana and so on, only reachable from our network. So I'm going to connect to my BPM. See if I don't have any. Yeah, looks good. And I need to point my Kubernetes environment var to this configuration, but I took care of that before. So we can go on with the demo and start using Kubernetes via kubectl. kubectl is the Kubernetes command line interface. It's basically working against the Kubernetes API. Is everything okay? Or? Yeah, okay. It's basically working against the Kubernetes API and getting the resources that we created in Kubernetes via calls to that API. Also needs to authenticate against Kubernetes. So we can see, for example, the nodes we have created. We have 6 nodes here. Since we are using EKS, we don't see our master nodes. We only see our worker nodes. And as I mentioned before, those nodes are resources also stored in a Kubernetes etcd. We see the IP of those nodes in our nodes network. We see the version of Kubernetes that they are running. We can also check the pods that we have running in our cluster, and we see that we don't have still any pod. And that is because in Kubernetes we also have another concept, which is the namespace. The namespace is, again, an isolation technique within the Kubernetes cluster that we can use in order to virtualize our cluster and have isolated spaces in which we can create pods and set up some kind of policies in order to restrict the access from one namespace to the other, and simulate also some kind of environment without creating different clusters, stuff like that. But if we say that we want to see the pods running in all our namespaces, we see quite some of them. I think it's big enough. So in here, if we look at these pods, you guys see some of the things that I've been mentioning in these blue boxes. We have an Elasticsearch cluster running. We have a FluentD daemon running on every cluster. This FluentD, for example, is a good example of another resource that we have in Kubernetes, which is called daemon set. Instead of the deployment, the daemon set ensures that we have a pod running on each of our cluster nodes. So it's to implement different patterns. To implement different patterns, we have different abstractions in Kubernetes, more specialized than the deployment. Daemon set is an example of that. Also, we have a stateful set if we want to have stateful applications. That's the case of Elasticsearch. We see here running as a pod also kubeproxy that we saw in our slides. This component we see over here, it's the CNI implementation from AWS. So this is the way that EKS has to implement the pods network. We have this component, the Share Manager, that I also mentioned before. So I'm not going to go over all of them. Our English controller. Let's go and deploy a Hello World application. To deploy this application, I'm going to create a deployment. So here we see the message that is telling me that my deployment was created. That means that I have an object in my database, a deployment object in my database, plus a replica set, plus other objects that are being created under the hood. We also see that I have created here another object called horizontal pod autoscaler. That's going to take care of scaling my pods, the pods I'm running in the cluster, when they get some load. I'm going to deploy also a service and an ingress controller. So if we check now my deployment, we see that we have 2 pods running in my cluster in the default namespace for this Hello World application. Let's go to have a look to some of the other things that we have installed on top of our cluster with this pipeline. So here we have the Kubernetes dashboard. We installed this dashboard via a Helm chart with some customization to make use of the external DNS component that we also have and the shared manager component that we also have. So this dashboard has a public available, not public available, but an actually internet available DNS and a valid certificate. This DNS is only reachable because I'm within this VPN. I'm going to show that later, so you see that it's not a trick. And to get into that dashboard, I need to get a token from my AWS, using this tool called AWS IAM Authentication. So I copy this token, and I can authenticate in the Kubernetes dashboard using my AWS credentials. I got that token because I have my AWS credentials configured in my environment vars. So here we see our Hello Kubernetes running. We see that we have 4 pods. we see that we have a replica set, which is a resource that I mentioned before that it's been created under the hood by the deployment controller. And we have our ingress. We have the service for this deployment. More things that are of interest to see in this example is that we have our Kibana Elasticsearch Fluentd stack automatically deployed, so we can see actually the logs of our applications. This is an annoying thing that we have to do the first time that we deploy this, but it's a 1 second thing, and you don't have to do it again later. So, and we can see, for example, all the logs of our cluster, of all the pods, of all the stuff running our cluster, even the Kubernetes system pods, like the daemon sets that we saw for the networking, for the CNI networking, and so on and so forth. We can do things like filtering by label, and say that we want to filter by hello Kubernetes. No, this is not here. In here I need to see this. And we see only the pods, the logs of this application. And we can, of course, build dashboard and use Kibana the same way you use it for any other use case. More interesting stuff that we have installed in terms of visibility, for example, we have a Grafana plus Prometheus stack. So I need to get the password for Grafana that it's as a secret in Kubernetes. Secret is another concept that we have in Kubernetes to store secret stuff. So, yeah, no, that wasn't very original, but so we can see things like reuse Grafana dashboards available out there and bring them to our cluster. I have set here some default dashboards in my pipeline, but we can extend them and modify them and so on and so forth. One thing we haven't seen yet is our Hello World application actually running. So let's have a look at that. And we have our Hello World application. Difference between this DNS and the other ones, this is going through our public ingress controller, that Nginx ingress controller. That means that we have two Nginx running in our cluster, one internet-facing, one only reach out from our VPC. So if I disconnect my VPN, I still can reach this, and you guys should be able also to reach this. On the other hand, my Kibana dashboard, I cannot reach it without my VPN. One last thing, I don't know how I'm doing about time. Who can give me some feedback about time? 5? Yeah. So let's do one last thing. So let's try to, no, not this console, this one. Let's try to scale, to make this application scale. So I have here a Kubernetes Manifest, which is going to run a deployment of 100 replicas. 100 replicas doing a card request in a loop to my Hello World. So I'm generating quite a heavy load in this example. So let's deploy that. Let me turn my VPN on again so I can see the dashboard. And let's watch for our pods to actually scale. So this should be working back again. It's not that cluster, it's this cluster. Okay, so we have created this load generator. We see that it's trying to create the 100 replicas, and it takes some time. Some of them are not ready yet, but we should see quite soon enough these horizontal pods, autoscaler working and creating more replicas for our pod. Eventually, what happens is that we will run out of actual compute and memory resources in our cluster. That means that our nodes over here are going to run out of resources, and our cluster autoscaler is going to start talking to AWS and spinning up more actual worker nodes, joining them to the cluster, and the scheduler will be able to start scheduling pods in there. So we see here that we are already going to 8. So our scaling experiment, it's working. I would like to stay here for a while in order to show you how this goes after 30 minutes and see AWS spinning up more nodes. But instead, I took a picture of how this looked like after 35 minutes. And yeah, it gets up to 800 pods, which is the max number that I put in my horizontal pod autoscaler. And of course, with this annoying user with 100 replicas generating a while true loop of requests towards our hello world, even though it's a very small application, the hello world, eventually it gets scaled. So this was it, now for good. So questions and